we do is understanding how energy landscapes occur in various optimization problems such as folding proteins and molecular clusters. And more recently, we are looking into neural networks and things like that. So before I joined David Wilson's group, he actually didn't do quantum computing applications. So we are quite pleased that we are able to explore what energy landscapes we can obtain using basin-hopping theory and the techniques that our group has developed so far. So why is it so? I'll just click with yeah, so basically this is kind of the framework as to how we analyze the energy landscape. So it comprises of four main parts. So the first part is basically mapping your Hamiltonians. So you have to convert basically your problem. If it's an electronic structure problem, you can express it in the second quantized form, and after that you can represent it in a qubit Hamiltonians for the quantum computer to interpret. Then afterwards, we will try and simulate this problem using an actual quantum computer. So we will need to prepare the initial state, and afterwards we need to do some ansatze with variational or not. And afterwards, what we can do is we need to optimize using LBFGS or some optimizer. So for us, we use basin hopping so that we can try and obtain as many local minima and other interesting stationary points. After that, we will basically iterate this between the classical and quantum computers until we reach some kind of convergence criterion. And afterwards, we can basically compile all sorts of local minima that we obtain here. After that, we can try and use this information to refine the ansatz that we have, basically.
And you find minima and stationary point connect stationary point.
Yeah.
You're just looking at that.
Yeah, so basically, we aim to also, from the local minima, try and find databases of connected minima, and we plot them and visualize them by means of these connectivity graphs, which I will show at some so these are some of the ansatzes that we are currently working on. So the earliest example is this hardware efficient ansatz, which is kind of problem agnostic, but it's quite efficient when it comes to encoding in the NISQ era. Then afterwards, I've looked into unitary couple cluster and QAOA problems, which for QAOA, we aim to solve the max cut problem for in combinatorial optimization. And most recently, I've been looking into quantum machine learning kind of energy landscapes and seeing what sort of how the performance of each local minima is with respect to classifying a given database. So I'll run through each of these examples. Yeah. Sorry? You don't see my... Oh. Why is it so... okay. Oh, does it work now? Okay. Okay, so the first example that I will talk about is QAOA. So it's basically a variation of the VQE that aims to find the max cut solution. So if you're given this 4-qubit graph, for example, and see that we can actually encode this problem using an Ising type model by the interactions between different vertices. So for example, this has a vertex of 1, so therefore we will encode it as a RZZ gate with minus gamma, basically. So gamma and delta are basically the parameters for this simulation. After that, we can actually increase the number of circuit layers in order to try and make our circuit more more expressible in terms of the number of parameters. So this is an example of a kind of a trotterized schedule, which which we simulate not only the cost Hamiltonian, which is basically encoded in the RZZ gates, but also using a mixer Hamiltonian that basically ensures that we don't end up in the ground state, which is our original encoding. So also a very important distinction between standard VQE and QAOA is, although we want to minimize the cost Hamiltonian, ultimately the product that we want is basically we want the highest probability of finding the max cut solution, which is as shown here. Yeah, so how do we visualize energy landscape? So if we take the L equals to 1 circuit ansatz, which comprises of only two parameters, gamma and delta, you can see basically this is kind of the 3D plot against the cost Hamiltonian. So basically for this example, there are two minima. So the green dot here is the global minimum and the red dot is the local minimum. And what we want to do is we want to simulate this for higher order energy landscapes, because obviously if we increase the number of parameters, we won't be able to plot contour graphs like this. So what we do is we actually group our minima into super basins, and after that we try and connect them based on the basin thresholds. So if we see in this example here, these are two minima, and we see which is the next highest energy basin. So that's why we will actually connect it here, for example. And from this super basin, we will actually connect it with this other super basin over here, and we'll connect it by this energy gap over here. So this is kind of how we represent this in terms of this connectivity graph for this energy landscape. And what we can actually do is we can also color the, sorry.
You choose the value of epsilon.
So the value of epsilon will depend on how large the transition states are. So for example, for QAOA, the local minima energy or cost gap is not that large, so therefore it's somewhere in the order of 10 to the power minus 1 arbitrary units. But when we go on to unitary coupled cluster, where we're dealing with very fine minima, we might be looking at 10 to the power minus 5 R3s.
So it's problem dependent.
Yeah. So it's dependent on the problem. And actually for machine learning, it's somewhere in the middle, like 10 to the power minus 3 arbitrary units. And I think a good advantage of this method is we can actually color our disconnectivity graphs with a secondary parameter. So in this case, what we do is we can actually color it based on the minima's respective probability of finding the correct solution. So for this example, the global minimum has a probability of finding the correct solution of 0.5, which is expectedly higher than the local minimum, which has quite a poor solutions probability. So what we do is we actually optimize this using standard LBFGS. So we need to calculate the analytic gradients for this optimization. However, fortunately, there's a very simple way of doing this, and this is by using the parameter shift rule for each individual parameterized rotation gate. And we also may need to check if what we are getting is actually a minimum. So we'll need to calculate the Hessian and figure out the number of negative eigenvalues for that Hessian matrix. Yeah, so basically this is kind of what we have done for complete unweighted graph. So basically these are graphs that every vertex is connected to every other vertex, and all the vertices are of weight 1. So we actually get some interesting results. So the top value over here for each individual cell is basically the number of minima, and the bottom value is basically the highest probability that we obtain for a given minimum. So basically, it's expected that as you increase the number of vertices, it becomes harder to find the the probability. So by increasing the number of circuit layers in the ansatz, we are able to get a more expressive ansatz, and therefore we can we can obtain better solutions overall. However, this comes at the down cost of the cost of actually increasing the number of minima. So we actually noticed quite a huge increase, exponential increase basically of the number of minima as we simulate this sorts of systems.
So the n equals 3, n equals 5, there's just one, is that one?
Yeah, so this is actually quite interesting case because we'll expect the number of minima to actually increase for n equals 5, but actually it becomes just 1. So we actually suspect that this has already reached the adiabatic limit for n equals 5, and it's possible that, you know, as L tends to infinity, we may actually only get one global minimum.
So does that mean your answer is sufficiently flexible that your surface is very nicely, smoothly connected with one single minimum?
Yeah, basically, yeah. Yeah, so this is a bit hard to prove because obviously you can't increase the number of layers infinitely and test each individual one. So this is kind of like a hypothesis at the moment. Yeah, but I think it's plausible that this might happen.
We use a number of degrees of freedom argument because in n equals 3, that's 6 degrees of freedom in the book.
Yeah.
And I don't know how you need to solve the problem in general.
I mean, we also want to find the minimum number of layers to reach the best probability, basically. So if accuracy is a thing, then probably L equals to 3 for this is good, because but at the same time you might have to balance the fact that you are running this on a NIST device with considerable quantum noise, so it's possible you may not get the optimal solutions from the increased noise as well. Yeah, so we can take a look at the disconnectivity graphs for the unweighted graphs basically. So we actually obtained quite good max cut probabilities for even minima that are quite high up in energy. So actually this has quite an important implication in running it on the quantum device. So this means that even if you were to land on some non-optimal local minimum, you're still getting quite a good probability of finding the correct solution. So therefore, this kind of showcases how the robustness of QAOA when running it on a NIST device from an energy landscape perspective. Yeah, so the next thing that I wanted to look for is what will happen if we were to run it on 3 regular unweighted graphs. So basically, every vertex is connected to 2 other vertices. So we took a this type of graph is actually quite common when it comes to QAOA research. So I wanted to see what sort of energy landscapes we get from it. So the results are actually quite interesting. So we can actually see that with the number of layers increasing, we can actually see there's there's this general trajectory towards moving to a good solution probability. However, at the same time, we actually see this greater proliferation of minima with not so ideal solutions, basically. Yes. Yeah, so basically it's just finding the probability of this state, this encoded state. So this is just 0, 1, 0, 1. So basically it's the probability of finding 0, 1, 0, 1 plus 1, 0, 1, 0.
Up to many runs that you've done, or out of the energy that it has?
It's out of the optimal solution you found.
Yeah. Yeah, right.
So it's just presumably square the curve in the state vector.
Yes, correct. Yeah.
Okay.
Yeah. mean, ideally, we also want to actually run this on a noisy kind of model, which actually is kind of like the aspect in which I want to look into during the PhD. Yeah, so we also took a look at this interesting case study where now we select this weighted graph where we actually had this graph with 4 vertices. The difference is that we actually change the value of this central edge here. So if it's 3, for example, we get we get 0, 1, 0, 1 as a solution. However, when we actually increase it to 4, basically now the correct solutions are 0, 1, 0, 1 and 0, 0, 1, 1. And for 5, basically it's just 0, 0, 1, 1. So therefore I wanted to see what sort of effect this will have on the energy landscape. So we can see that actually we obtain quite a well-funneled energy landscape as usual. However, we actually see I would say a more strained sort of system in which the minima that are further up in energy are they actually have not so ideal probabilities basically. So and of course an exception is the one with central weight of 4 because there are more solutions for this, so therefore it's not as drastic as the center weight of 3 or 5, for example. We also noticed something pretty interesting in which the global minimum actually may not have the most optimal max cut probability. So we see here with the disconnectivity graph for L equals to 1, we can see that the global minimum here it's around 0.25, whereas for the next highest local minimum, it actually has a higher probability of finding 0.5. So therefore, this suggests that there could be a family of graphs out there that display this sort of behavior in which the global minimum may not necessarily translate into the best max cut probability. Yeah, so this is kind of the scatter plot of the 3 graphs against the circuit layer, the number of layers in your ansatz. So red is alpha, beta, and then blue is alpha, beta. So for the center weight of 3, basically the best probability is here, and then we can see that actually for the competing solution, this is somewhere around here. So we can actually establish some sort of expectation cutoff that we can say, okay, these minima over here, they basically correspond to a good solution probability of finding alpha, beta, but not alpha, beta. So in a sense, we can actually use this knowledge to estimate what sort of expectation cutoff we need to establish to obtain a good solution probability. So again, this is also useful when it comes to running it on a NIST device. Okay, so now I will talk more about intercoupled cluster ansätze. So basically, the difference between simple hardware efficient and intercoupled cluster is we actually take the excitations and the excitations in the electronic structure of the molecule into consideration. However, in practice, when we actually try and do this, it's more computationally intensive because the circuit is considerably larger than hardware efficient. So we basically want to do UCC. So for standard UCC, we take into account the single and double excitations. So I'm currently collaborating with Andrea Philip, who is a postdoc in Germany at the moment. So we basically formulated this means of computing the ground state energy of a molecule using the UCC formalism. So basically, we kind of utilize these 3 cases to evolve our state based on the different operators that we have. And we can actually calculate the analytic gradients quite easily by for the optimization. So we actually work backwards to calculate the energy. So the result is that our calculation is much more efficient. And similarly, we can also do this for the Hessian matrix. So in practice, you can convert your UCC operator into a quantum circuit so you can simulate it. However, in practice, it's really very computationally intensive. So what we did was we actually took the excitation operators and we evolved our Hartree-Fock in accordingly. So what sort of we actually get for hydrogen, for example, this is the exact FCI basically, which is nothing unusual. We also did this for lithium hydride and for nitrogen with 12 and 16 qubits respectively. So basically the ones with asterisks are the ones where local minima were also present when we simulated it, and therefore we sought to basically plot the disconnectivity graphs for these examples.
Q.
Q is the number of excitation operators. So for lithium hydride, we did a maximum of 34, which is basically the standard UCCSD, and for nitrogen is 53.
How do you
excitation.
choose? How do you select the excitation?
Yeah, so those were based on the order by the Evangelista paper. Yeah, yeah. So basically, for this one, for example, it's basically a subset of these 34. Yeah,
But the like the largest number is all of them.
yeah. So we actually obtained some interesting graphs for lithium hydride. So we actually get this sort of banyan tree kind of appearance, where actually the energy, the local minima are separated by very large barriers of energy. So you can see that this minima and this minima, so there are about 8 minima here. So any two minima are actually connected all the way up here. So basically we are looking at really large separations in terms of energy. So it's so in a sense we are actually dealing with very glassy sort of energy landscapes, which makes basically optimization quite challenging when it comes to UCC.
What's the difference in energies between the actual minimum themselves?
So for this example, it's about 10 to the power minus 5. However, when we go on to nitrogen, basically the energy gap is quite significant that basically any two minima within this lower shelf is actually higher than chemical accuracy. So what this means is that even though you might get an energy from over here, you might still be quite far off in terms of energy from the true global minimum, and it's not easy to escape out of this energy gap because they're quite large with respect to the energy gap down here.
And on the left, is there any sort of symmetry relation that maps one of the little clusters to
Yeah,
the other?
I actually tried to find some sort of symmetry, but I couldn't really. It's kind of mixed. So I don't know. maybe that is for the 20 operator one. So it's actually, yeah, that's something I'll probably look into.
Well, numerical type are you evaluating everything? So you need float, double.
It's a double. It's in terms of energies.
But like internally when you do the quantum calculation.
Yeah, so everything is in terms of double, so there are no imaginary units. So just cosines and sines.
And you're getting that out of the thetas, and you reverse engineer what the wave function is. You
Yeah.
actually able to speak to it.
Yeah.
Yeah, probably. Reasonably. I mean, I'd imagine you can do that to decent precision. But
Is there a change in the picture? So you've been working on this in the fermionic representation.
Yeah.
Do you expect any significant changes when you go into Pauli representation?
I don't think there will be that much difference, to be honest. Yeah, because at the end of the day, we are just doing the regular excitations. whether it's the fermionic or the Pauli formalism. Yeah, so as I mentioned, basically within this lowest neighborhood of energies, basically the local minima, they are very close in energy to the global minimum. So it's about 10 to the power -5 or -6 trees. So basically the vast majority of the local minima, they are much higher in energy, and as we increase the number of operators, basically the number of local minima increases exponentially. So basically this has only about 800 minima, but this has like 200,000 minima, and this is probably not this is basically the energy, the discontinuity graph that I obtained. So the true number minima might be much higher than this.
And so in terms of parameter, are the parameters very different from each other when you end up in one of these minima? And are the wave functions very different, which could be a different?
Yeah, so the wave functions between the neighborhoods, they're not that much different from each other. Between different neighborhoods, I would say they are different. So I will probably plot this against the overlap of the FCI versus probably that'll be more informative as well. Yeah, so we actually observed that from the amplitudes that we get from this optimization, the energies over here, the amplitudes here, they typically are somewhere very close to 0 and ±pi. So therefore, we wanted to color this based on the following metric, where we actually take the minimum distance between 0 or ±pi, whichever is lower. We will actually compute this in this metric over here. So we can see that generally all the minima found here, they are very low d values. So they are quite close to 0 or ±pi. Whereas for these minima over here, they actually have some that are in that are close to pi/2. So this means that probably for these minima, your wave function is not sufficiently evolved.
Is it the equilibrium boundary?
So this is for 1.5 angstrom. Yeah. So this is for close to the equilibrium boundary. We also did one slightly further away. Yeah, but basically the landscape looks quite similar for both sets of both bond lengths of lithium hydride. Yeah, so this is actually the distribution of the minima that we obtain versus and also the d value. So we can actually see that actually there is a general shift towards better sort of energy. So what this means is that globally it's easier to find overall good solutions, but locally it's going to be more challenging finding the needle in the haystack, which is basically where the global minima is from this neighborhood over here. Yeah, so we actually also calculated the heat capacities for lithium hydride. So basically the main peak you see over here is basically the transition between this lower neighborhood with all of these minima with higher energies, basically.
These heat capacity, effectively, you take each of the solutions, each
of the energies,
and then you weight that as if it were one of the microstates.
Yes.
And that gives you a heat capacity.
Yes, correct. Yeah, so basically the main peak over here is basically the transition from the lowest energy neighborhood to higher neighborhoods, while the smaller peaks you see over here are basically the transitions between within the neighborhoods, basically. So we actually observe for the 34 operator, it's higher because there is a greater proportion of higher to lower minima. So it's also sharper because the energy gap between the higher and the lower states is smaller as compared to the 20 operator one. So So therefore, yes, so this ties, so the main takeaway is that it's globally easier to find an overall solution for, you're actually getting better approximations for the energy for a 34 operator case as compared to the 20 operator case. However, the so locally it's going to be more difficult to find the global minimum within the lowest energy neighborhood, basically. So we actually did this for nitrogen. So we can actually, so this is where we actually observe that within this lowest neighborhood, the energy gap between these two minima may be higher than the threshold for chemical accuracy. So this is actually quite significant because because when someone does the simulation, for example, they may think they actually got the solution based on when they land on the neighborhood. However, it may not actually be the true global minimum, and it's not easy to, to go all the way back up here again and do the optimization. So it's more challenging as a result. Yeah, so this is also this. So this is the frequency of the minima. So we can actually see that there's a general trajectory of improving solutions. And then finally, I've also plotted the heat capacity. So for the 11 operator case, there are only two. It's quite a simple system. However, for the 33 and the 53 case, we actually see more complicated peaks because of the more complex energy landscape that we obtain. Okay, so finally, I will talk more about quantum machine learning. So basically, what we want to do is we actually want to simulate basically machine learning techniques onto a quantum computer. However, it's important to note that it's remains to be seen if we can actually find some sort of quantum speed up by using a quantum computer. So I guess right now we are in this phase where we need to narrow the scope of quantum machine learning. So for example, we need to ascertain what makes a good ansatz, what makes a good data encoding, for example. So basically for the quantum variational classifier example, it's quite similar to how we would do it on a classical neural network. So if we are given a data set with input features x and size m, so basically we will actually input this in our input layer in a classical neural network. In a quantum computer, we will actually load this first in our feature encoding circuit. And the aim is to actually predict what is the class of that given vector xn, for example. And we actually do this by means of a variational ansatz with this operator here. So it's actually analogous to the hidden layers in a classical neural network. After that, we want to find the class of that particular point that we have. So in the quantum computer, we will just measure the state and find out what's the probability of finding that state in the computational basis. So for this example, I'm using the cross-entropic loss function. So it's just the class times the log of your probability. So this probability it has undergone a sort of softmax in order to kind of normalize the loss function, and we actually divide it over all the data points that we have. So we can actually calculate the analytic gradient for this. So basically, we can actually separate out this using chain rule. So this del L over del E is quite a standard form in classical machine learning. So basically, it's just the probability minus the class, basically. And for this del E over del theta, we actually saw that it's just the same form as the parameter shift rule. So how do we encode the probabilities to the class that we want to predict? So basically, this is kind of like how Qiskit does it, but we just take the computational basis cat and we actually map it to 2 to the power of n mod k. So k is the number of classes, basically. So what this means is that for example, for this iris set, there are 4 qubits. So for all the computational basis, we actually map the probability of 0000 to class 0, and then 0001 to class 1, and then we continue. Once we hit 2, we actually just reset the encoding.
Why choose that encoding? Because it seems quite scattered.
It's the most convenient way. Yeah, I mean, there's also an open question on what makes the best encoding. So is this ideal? Yeah, so this is something that I'll probably look into at some point. Yeah, because so unlike UCC or QAOA, there are actually a lot of things that need to be considered. So what makes a good encoding? What is a good ansatz? And what sort of what sort of output encoding do you want to use? So all these parameters actually make ascertaining the parameters of quantum machine learning quite difficult. Yeah, so for this one, I actually use a iris data set. So it's quite a simple data set with 150 data points with 3 classes. So for this, I did a 80-20 split. So the 80 is basically what the training data that I used to train the model on, and 20 is basically the testing class. So there are there are 4 parameters for this data set. So for simplicity, I just took the number of parameters as the number of qubits. So this is kind of like the ansatz that I tried. Basically, it's just a simple RY gate and this linear C naught sort of encoding. So this is so this LX over here is basically the data encoding section of the circuit, and over here is your variational ansatz. So the aim is to actually optimize the loss function with respect to theta. So we actually get some interesting disconnectivity graphs. So as we increase the number of layers, so very similar to QAOA, we actually see that the number of minima also increases. However, interestingly, unlike QAOA, we actually see that the local minima over here, they tend to have also pretty good probabilities as compared to the weighted 4 vertex graph.
Like anything, well, it's good. Just picking any of those.
Yeah.
Gives you one.
It's like 0.93. Yeah. So if we take a look at this scatter plot, we can actually see that the training scores are actually pretty they are going towards a more towards a nicer training score as compared to QAOA, where as you increase the number of layers, we actually may get some minima over here with bad solutions, for example. So overall, this means that the standard deviation for finding the training or the testing score is actually going to be smaller overall. So therefore, and also the fact that the global minimum actually does not correspond to the best classification accuracy again, such as compared, which is very similar to what we get at QAOA. And we can actually use this information to find what is the minimum number of layers to reach the a good solution, a good score, for example. So this is actually important because we don't want to have too many layers, because for 2 reasons. So the first is you actually will increase the number of minima will actually increase as you increase the number of layers, but also the fact that in machine learning, a very important aspect is to also reduce or eliminate the possibility of overfitting. So if you increase the number of layers, you're actually you may actually make your ansatz too expressive, and therefore the model may not be able to accurately classify the data. So in a sense, it's overfitting. So in this case over here, we actually see that for L theta equals to 4, we actually can get a good classification score. So I'd say L theta equals to 4, it has the least chance of overfitting, but at the same time, you're also getting quite a good test score when you are doing this classification. So again, we can really use this knowledge of energy landscapes to give us a understanding as to how many layers we can select when it comes to quantum machine learning tasks. Yeah, this is the last slide. Actually, the second last slide. So basically, for future work, we want to, basically, we want to survey the entire variational algorithms that are out there. So there are other quantum machine learning algorithms such as quantum kernels and regression that I want to look into. I'm also looking into folded spectrum with Lila so that we can actually basically obtain not just the ground state energy but also excited states of various molecules. And also an interesting idea that I thought about is, can we actually encode molecular fingerprint using using a circuit, for example. So in this like rough sketch here, basically this unitary is just for this carbon-carbon bond. So we actually, so if it's a double bond, for example, we actually just double it basically. If it's a triple bond, we just triple it. So I think I don't know if this is feasible, because it's possible that the reordering of, if you reorder the number of atoms, you're also reordering the circuit. So and these gates here, they are not interchangeable because you get a different wave function. So I don't know how's the feasibility of this. So I probably need to look into this at in greater detail. And then finally, we can also, so an aspect that I want to work with is also quantum noise, and also how we can use quantum mitigation techniques such as zero noise extrapolation to try and reconstruct the energy landscape using a quantum computer. So I'll to thank my professor David Wales for giving me this opportunity to understanding his area, and also and linking it back to quantum computing. I would like to thank Andrea for her guidance in the UCC portion of the project, and also to the Alex Tom group for the plenty of discussions that we had on quantum computing, and to my colleagues as well.